Welcome to the second lecture. In this lecture, we'll study voltage transfer characteristics of a CMOS NOT and will derive an expression for the middle voltage Vm. In the last lecture, we studied some basics about CMOS and about CMOS NOT, and we established that this CMOS NOT is perhaps the simplest circuit that we can implement using the CMOS technique. And using the CMOS technique, we can implement any given Boolean expression with equal number of PMOS and NMOS transistors. Right. In this lecture, we're going to study a voltage transfer characteristics (VTC) of a CMOS NOT. In fact, we'll study VTC of CMOS NOT. To draw this VTC curve, actually this is VTC. To draw this curve where we have V in on the x-axis and V out on the y-axis, to draw this curve, we have to apply DC analysis, and DC analysis is performed by applying the full range of voltages between logic 0 and logic 1. So we are working with a system where logic 0 is at 0 volts and logic 1 is VDD. VDD can be 5 volts or even smaller. So we apply all the voltages between 0 and VDD and we check the output, of course. Apply the range of voltages between logic 0 and logic 1 and we observe the output. And finally, once we have this table filled in, like we'll have to implement this table like this. We have V in, V out. The table would look like this. We apply 0 volts, we note the output. We apply maybe 0.1 volts, we note the output. Maybe we apply 0.2 volts, we note the output, unless we apply VDD and we note the output. So this table would look like this, and finally we translate this table into this graph where we have V in plotted on x-axis, V out plotted on y-axis. Right. So on this voltage transfer characteristic curve, and we call this as VTC, voltage transfer characteristic curve. Why voltage? Because we have voltage at the input on the x-axis, voltage on the y-axis, therefore voltage. And why transfer? Because one of the quantities, the input voltage, we have taken it from the input of the gate, and the other quantity V out is from the output of the gate. That is why this is transfer. And of course, this is a graph representing some characteristics. Right. So V output high is the actual voltage in volts when the output is at logic 1. When the output is high, it's the actual voltage in volts. Suppose we are working in a system where, for example, we are working in a system where we have, suppose VDD is equal to 5 volts. So this is actually, if VOH is actually, if it is maybe 5 volts, so we say that VOH is 5 volts. If the output voltage, when the output is high, if you measure it using a voltmeter, actually we know the output is high, and we put a voltmeter here with respect to ground. We measure actual voltage at the output. If this voltage is, for example, 4.9 volts, we call it VOH is 4.9. So for most CMOS circuits, this output is VDD, is equal to VDD. V output high, it's the actual voltage in volts, and it is equal to VDD for CMOS circuits. VOL is actual voltage in volts when the output is at logic 0. When the output is at logic 0. So this is actual voltage in volts when the output is at logic 0. Right. So if we are working in a system where where logic 0 is 0 volts, and for example, if we have this logic 0 at the output for a given circuit, for a given input, and it is set as maybe 0.1 volt, we call it VOL is 0.1 volt, but it is logic 0. So VOL and VOH are not logic voltages, they are These are not logic levels, these are actually voltages. Voltage is measured in volts. VIL is also a voltage measured in volts. This is the input voltage corresponding to the first m is equal to -1 point, where m is the slope. M is the slope, and that is delta y over delta x. So somehow if we have like this, if we have delta y over delta x, so if delta y over delta x is -1, this actually on this curve we have two such points where we have delta y over delta x is equal to -1. This is the first of these 2 points, and this is the second point. So the common characteristic of these 2 points is this point and this point, is that if we draw a tangent line slope m is equal to -1, that will actually pass through this curve, that will touch this curve only at one point. That will be actually the tangent that will be tangent to this curve. So m is equal to -1 line tangent to this curve is at this point and at this point. So these are the 2 points where m is equal to -1 line makes a tangent or draws, or it intersects this curve only at one point. It's a tangent to this curve. So this m is equal to -1 is tangent to this curve at 2 different points, at this point and at this point. So V input high is the input corresponding to the second m is equal to -1 point, and Vm is the middle voltage. This is the voltage corresponding to m is equal to +1 line, or it's the point where Vin is equal to Vout, or it's the point on the curve where we have Vin is equal to Vout. I told in one of my earlier lectures that if you are asked to walk on this curve starting from this point and you go down this curve, at this point you'll see you'll have output Vout greater than Vin, because Vout is around VDD but Vin is quite small. This is Vin. So if you go down this curve, suppose once you are here, you see once again your output voltage is higher than your input voltage, and if you keep on walking, and suppose you can walk on even at the steepest point on this curve, although it is difficult, but at this point you see your output voltage is smaller. Your output voltage is smaller compared to your input. Your input voltage is higher. At this point, of course, your input voltage is very high compared to your input voltage. So for some of the points, for example this point, this point, and this point, for these 2 points your output voltage is higher than your input voltage. For these 2 points your input voltage is higher than your output voltage. This means there must be some point, because you are walking down this curve, so there must be some point where your input voltage is exactly equal to your output voltage, that is Vm. And we can mathematically draw, we can mathematically calculate this Vm. We can mathematically calculate this Vm, as well as we can show it on the curve too, right? So the last two quantities that we derive from this VTC are the noise margins, noise margin low and noise margin high. Noise margin give us a quantitative measure of how resistant your inputs are into the electromagnetic EM noise in the circuit. So this should be very large. The larger these noise margins are, the better it is. The better it is. So NM's noise margins, we call them noise margins. So noise margins should be, they must be large. So larger noise margins means larger resistance to the EM noise present in the environment. We calculate two noise margins, noise margin low and noise margin high, indirectly from this VTC, this voltage transfer characteristic curve. Noise margin low is V input low minus V output low. We know V output low is almost zero. It's for CMOS, it's always equal to zero. So VIL is somewhere here. So if it is large, this margin is large, that is good. But and noise margin high is V output high minus V input high. V output high is almost fixed because it's equal to VDD. V input high is this voltage. This should be large. For that should be large, this V input high should be small, because in order for this difference to be large, this should be small. And in order for this difference to be large, V input low should be high. So ideally it should be like this. Ideally speaking, to have noise margins, very large noise margins, that is the desired thing. So to have very large noise margins, we must have some characteristics like this. Maybe this is VDD and this is VDD by 2. So to make these two noise margins large, and this should be equal to V input high should be equal to V input low, should be equal to VDD. So this is the case where we have both noise margins, noise margin low and noise margin high. They both are very large, because VIL and VIH, they both are equal to VDD by 2. This is 0, so this would be VDD by 2 minus 0 equal to VDD, and this is VDD minus VDD by 2. This is also VDD by 2. So this is the case where we have both equal to VDD by 2. They both are large. So this is somewhat ideal, but it's actually ideal. Practically the curve is like this. So we have some different VIL and VIH. Right. In the next lecture, we are going to derive. In the next lecture, we are going to derive mathematically an expression for VM, the middle voltage. We'll start from the basic drain current equations, and we'll reach at a point where we'll numerically or mathematically compute the actual value of VM.